What's going on, everyone? I don't know how many people are currently here right now, but it looks like we just lost James, so I'll be flying solo for a little bit here. I apologize for half the screen being black for or blank for a little bit here, but definitely excited to talk to people again, especially about this video. There's a really good turnout for this video. I think we're on like 600 views right now. A lot of new people to the channel, so it's definitely an honor for people to watch my videos. I'm glad people are liking them. For those of you who don't know, I guess I don't think I've ever said it. My primary research is in condensed matter physics and the foundations of statistical mechanics. But in principle, like a lot of this research from day to day is, really heavy duty, computational physics. It's just, the problems that I'm interested in are foundations of stat mech and condensed matter physics. So there's a lot of a lot of my days are filled just looking at C++ code, trying to figure out new algorithms, trying to be more efficient with my code, and learning new things, and this sort of gives me access to the problems I'm interested in, because a lot of these problems are, when you talk about eigenstate thermalization, for example, there's no the models that you're interested in are, in general, and in particular, not solvable. They're called non-integrable models. And because of that, you need these large-scale codes, basically always. So the last year of my life, for example, has been doing these block diagonalization codes with a particular model in mind. I'll have an article coming out about that shortly. Hopefully shortly. Things with research papers are always they always get delayed more than you think. That, like, if you think it's going to take a month, it's probably going to take 2 or 3 months to finish up the paper, because there's always loose ends, and people have sort of, when you're at the point where you're writing a paper, people sort of it's not that they lose interest, it's that they've mentally checked out because they're working on new things. So it can sort of be hard to get people motivated to get back into projects when you hand the paper off to them, or like they're busy with other things that are mentally taxing. So it's tedious to write a paper, right? Like you want to say everything that you should say, and so on. So it's a process. So hopefully that paper comes out sometime soon. You guys can see the. Perhaps I'll make a video talking about this exact diagonalization code and sort of what we accomplished with it. Perhaps that'd be an interesting video. So I thought this video might be interesting for some people to sort of get a glimpse into what research might be like. I'd definitely be interested in hearing what people think about computational physics, or sort of the reality that it's very difficult to do hard physics problems without at least some form of coding. But yeah, I don't think I've heard from James. Let me send him a quick text here. Check Zoom. Oh, what? It didn't load properly. Okay, so I need to fix. Oh. Hello? Okay, so now I can't hear James. Technical difficulties here. Were you here this whole time? Uh, okay, yeah. So sorry, folks. We're gonna. I don't know why I can't hear James now. So, give me a few minutes. I was just monologuing there, waiting for James to log back in. He was here the whole time. Why can't? James, are you sure your microphone's working? Let me test. Oh, okay. I can hear you. Can people in the chat? Can you hear? Can you hear James?
Can you hear me?
Yeah, I can hear James now. Yeah.
Okay, I can hear you as well.
Okay, so we're back. I was just telling probably the Void about my new paper coming out with my large ED, or perhaps you. Perhaps I was telling you without realizing that you were still.
Yeah,
here.
so I was listening to I was listening to it's that is am I I'm audible here?
Yep.
Oh, swell. Um,
So hey Gabriella, hey Yule. It's nice to see you guys.
welcome to the stream. Good to see everyone back.
Yeah, it's a good it's a good time. So the interesting thing about today's video was sort of this like I don't know if it's a teaching moment, but I was sort of taken aback when this professor told me that like basically the only research that's interesting that's happening right now is computational work. And of course, as I said in the video, I definitely don't think that's true, but there is a real limit to analytical work. And as an undergrad, I came in and, I was really under the impression, as a naive undergrad, that you could just sit down and if you tried hard enough and you were smart enough, you could just solve anything. And like everything came down to analytics and, that's just what physics was. And that's obviously not the case. So I was wondering, did you have a similar experience or were you less naive than I was as a first year or a second year?
I guess maybe I want to say a couple of things about that. So I suppose maybe it's worth thinking about what we mean when we say solve a problem. I think it's before I studied physics in my undergrad, I was very interested in physics, but I hadn't really given too much thought to what it sort of meant when we said something like this problem is solved.
Yeah.
What does that really mean? And I think that in the analytical domain, what we find nowadays is that perturbative methods that make various approximations that are, we say, well controlled. So approximations where we can understand exactly how the approximation fails and quantitatively why it fails.
Yeah.
This sort of dominates the school of analytic physics nowadays. I wouldn't say it's the only thing that people are doing, but that's a lot of what people are doing in non-trivial problems. And I think that it's meaningful for us to say that, that is a solution on some level.
That's fair.
That set of techniques does get us answers that we can compare to experiment, that we can use to understand the physics that's happening, say, at a phase transition. So I think that absolutely there are analytical methods. There's a vibrant community of analytical methods that attain a kind of a solution to a lot of these problems. And we just have to sort of be clear about what it means to solve the problem. So, in the context of the video that you put up today, there are definitely a lot of problems where getting a sort of exact closed form solution is just not going to happen.
Yep.
And people really do accept that solving the problem in that sense, solving the problem in the sense of I have this function, it's exact to all orders, there's no approximation behind it, and it gives me the exact quantity that I'm interested in, maybe the expectation value of an observable in an experiment. Definitely those problems are kind of, for the most part, solved at this point. And
yeah,
like you mentioned, we need to rely on either numerical techniques or on this family of new sort of high-tech analytical techniques that involve making various kinds of approximations that are well controlled. But even within that family, the thing is as well, right, that physics problems are not monolithic. As anyone who studies physics, as you well know, and as many undergrads who watch your channel will be learning, there are many different flavors to physics problems, and there are many different things that we're trying to compute. And sometimes solving the problem looks like coming up with a new mechanism.
Yep.
So for example, in the case of, you mentioned in the video, the insulator superconductor transition, that's an extremely interesting topic at the moment. There is a mechanism that was proposed in the 1950s to explain what we now call conventional superconductors. And beginning in the later half of the 20th century, people began to understand that there are superconductors for which this physics simply can't be the correct explanation. And so the quest is on to propose new mechanisms that generate superconductivity. And indeed, there's actually some recent work I believe by Liang Fu, where he and his collaborators propose a novel mechanism for superconductivity in these non-conventional materials.
That's really interesting.
And they treat that mechanism using a number of approximations, using numerical techniques. So they sort of bring to bear a large number of different techniques. Oftentimes, especially if you're going to propose a solution to a big problem, you're going to bring numerical techniques to the table. You're going to bring analytical techniques to the table. You're going to use them to corroborate one another. It's common that if someone introduces a new numerical algorithm and you're reading a paper that introduces it, they'll benchmark that algorithm to tried and true methods like exact diagonalization or DMRG.
Yep.
So I think that, what we want to imagine is that there's now a sort of family of techniques, and what solving the problem really looks like is understanding the physics. And we now just have many roads to get there. Some of those roads are computational, some of those roads are analytic.
Yeah, so that's definitely fair, and I think it's also worthwhile to point out that there's also a vibrant mathematical physics community that contributes things like no-go theorems, for example.
Absolutely.
That sort of narrows the field of like where you should be looking for specific phenomena, and of course they do many other things like very very important bounds like the Lieb-Robinson bounds. But I guess the core of the question is sort of, so I guess you did answer it. You said that you never really gave it sort of a thought. You didn't have a preconception coming into physics. But I guess being an undergrad, I sort of, and I guess people in the chat can comment on how they were. Being an undergrad, coming in, you talk, you watch like guys like Michio Kaku or sort of Sean Carroll, the big popularizers of theoretical physics. I sort of came in and I just thought that was all physics was. It's just beautiful equations, and you're just fooling around with them all day, and you think about it, and interesting, like, as you sort of go along in your physics education, you start seeing, well, actually, it's really interesting to do things like Taylor series expansions in a lot of physical situations, because it's because you're really interested. You have these really complicated equations that you probably can't solve for everything all at once in the sort of the general form. But if you're really interested in a specific physical problem, it's just that's just sort of like the evolution of my ideas of like what it meant to do analytics. That sometimes like we're often very interested in very specific problems, and that's probably a big chunk of research is that, and that is certainly as worthwhile as in many cases as trying to find a general solution. But both are obviously powerful and useful.
Yeah, and I think that there's something here that's kind of maybe interesting to. By the way, Oil Franz, your comment in the chat, that definitely.
Yeah,
I think the experience of being recalls my own experiences as an undergrad, and I'm sure same for mine. I think there's an interesting question here about the relationship that we perceive between theoretical physics, mathematical physics, and what physics is actually sort of about and what we're trying to sort of achieve. I guess one take would be that I don't think this is a very controversial thing to say, but I guess one take would be that the business of physics is the business of making predictions that are then verified in an experiment.
I think that's complete. Yeah, I don't think there's anything controversial about that.
I think no, there's nothing too controversial about that. I think that some people would argue, and I think convincingly, that in addition to making predictions and comparing them to experiment, we want some sort of cohesive story that allows us to understand the connections between different experiments, the connections between different physical phenomena. I had a professor of quantum mechanics, Norbert Lütgenhaus, and at the beginning of our quantum mechanics course, he sort of described what he perceived to be the three phases of developing physical theories. And he said the first phase is you gather data on the phenomenon. The second phase is you distill out some set of mathematical relations that can take data as input and make successful predictions. And the third and the final step is to distill from that mathematical framework a key set of physical laws or principles. This was his sort of picture of physics. I don't know if I totally agree with that as being the full story. I think that there's actually a lot of, and I'm sort of quibbling here because I'm not really qualified to speak on this. There's a sort of large school of philosophy of science that asks this question: what is science really doing? How does the project of science relate to the real world? And by the real world, I mean the external world, the objective world. How does science relate to truth and so on? These are questions that people have discussed and debated for a long time. And it might seem like a sort of non sequitur to bring that up, but I think when we ask the question, what is solvable in physics? What does it mean to solve something in physics? What does it mean to explain a physical phenomenon in physics? This really is the kind of question that we're getting at. We're getting at this question of what does it mean for a theory to work? What are we asking for from our physical theories? What is the sort of metric of success for a theory? For example, you were mentioning in the intro there that we call these models that aren't solvable, non-integrable models. And I think it's interesting and kind of revealing of this point that even models that are integrable. So an example of this for the aficionados would be, for example, the spin 1/2 Heisenberg model.
Yep.
This is a model that can be solved by a technique called the beta ansatz. And in principle, this technique allows you to learn everything about the model that you're studying. Most specifically, it allows you to get the eigenenergies of the model quite straightforwardly. But the problem is that the computation of anything more than that, although in principle it is possible, is so difficult that if you're going to study that model, you're probably just going to use a Monte Carlo algorithm to study it.
Yeah.
And so, what does it mean to say the beta ansatz solves the model, right? In some sense, it solves it in principle, but in practice, the way you're actually going to work with this model a lot of the time is with something like a Monte Carlo algorithm, especially at finite temperature, where the beta ansatz is very cumbersome to work with.
So this is a really interesting point, and perhaps we could get into something sort of controversial here, because when you something that's sort of cooked into your education or the way a lot of people perceive physics is that the more there's sort of like a hierarchy of contributions when it comes to things like solving the spin 1/2 Heisenberg model with the beta ansatz or looking at it with like a very sophisticated Monte Carlo algorithm. There seems to be like a hierarchy where people assume that the sit down and write the math down by hand is somehow much more important to the story. But I mean, all avenues of investigation, in my eyes anyways, feel equally important. So I wonder if you can comment, what's your take on the perceived hierarchy of avenues to research physics? And I don't think it's controversial to say that there are a fair amount of people who do say they share these feelings sort of out loud, and I think the literature reflects that as well.
I think that's a good point. I'm reminded of another professor's comment, James Taylor, astronomy professor at the University of Waterloo, and I remember once during a lecture he was bemoaning the fact that people don't think of numerical solutions as solutions. Yeah. And his argument was, of course, they're solutions. I mean, they're giving you the answer. That's what it means to solve a problem. And I think that the camp that is, I'm not going to say opposed to that position, but the camp that tends to be dismissive of numerical solutions is sort of the camp of people who are looking for a cohesive story.
Yeah.
I think there's a sort of prevailing sentiment, and I don't even know if the sentiment is really false, but there's a sort of prevailing sentiment that when you come up against a problem that you don't have an easy answer for, that is an opportunity to come up with some new idea, some new technique, some new mathematical technology to get you that sort of straightforward, clear answer and thereby elucidate new physics. So maybe an example that I could offer of this is that in modern condensed matter physics, I sort of alluded to this last week when we were chatting, we rely a lot on this picture of quasi-particles and collective excitations. So we imagine that the physics inside of a material, the ground state of the material, is kind of like the vacuum state of a universe with symmetries and dimensionality possibly quite different from our own, maybe a one or two-dimensional universe, maybe a universe with a sort of square lattice geometry instead of continuous spatial and rotational symmetry. And we imagine that the ways in which the material is perturbed away from its ground state, the ways in which it can oscillate away from its ground state, are sort of like particles living in this universe. And this conceptual framework opens the door to a whole family of perturbative approximation methods that we sort of import from particle physics with great success. We use these methods to, for example, correctly and very precisely predict the way that the material will behave at a phase transition. We use them to predict things like the response of the material to a magnetic field, to a neutron beam. And so, this set of techniques, this technological innovation, importing this technology from particle physics, doesn't just let us compute the problems, but it gives us a sort of coherent conceptual framework with which to understand the problem.
Yep.
Now, by contrast to that, if I'd never thought about that before, and I just went ahead and did Monte Carlo on these systems, I would get the same predictions. I'd predict the magnetic susceptibility. I would predict the maybe the structure factor or some other quantity that an experimentalist might measure. But I would be lacking that conceptual framework that this analytic technique offers. And so I think all that to say that the reason that people sometimes tend to disparage computational solutions, I think, is really coming from this perspective that having an analytic framework to think about the problem in offers some additional notion of what's sort of going on, so to speak.
And I think Yule here in the chat is basically saying what you just
I think this is exactly the point Uwe's made. Yeah, I definitely agree with this point that Uwe is making. I think that really is what people are thinking about when they. Now, I think there's a meta question we can ask here, which is, and maybe this is really controversial. The question is, does that analytical picture, is that really true anyway? Is that analytical picture just a convenience, a sort of subjective anthropocentric convenience? And we're human beings, right? The theories we make are going to be catered to our intuitions about what it means to understand something. There's just no way to get outside of that fact. I mean, we're the ones doing physics as human beings, and consequently physics will be subject to, I'm going to sort of say, the aesthetic preferences of humans for what theories should look like. If we say that the only benchmark of scientific success is the ability to corroborate an experiment, then we wouldn't choose between computational solutions and analytical solutions. But I think what Will is driving at here, and what those people in the field who maybe prize an analytical explanation are driving at, is that we are looking for more than just experimental predictability. We're looking for a sort of coherent picture of what's happening, whatever that might mean. I mean, whether such a picture is even possible, there's a sort of philosophical school of thought that I'm rather interested in. I believe that they call it a pessimistic meta-induction. And so this is a sort of anti-realist theory of science. And what it basically says is, a long time ago, we believed in things like the Ptolemaic model, and we believed in things like the plum pudding model of the atom, these ontological statements about the universe, which we now think are ridiculous in light of new evidence, new theories, and so on. And that's just how science works. One day, everything we believe about gravity, everything we believe about quantum mechanics will be upended by a new, deeper, more explanatory theory. And people will one day look back on the people who believed that there was such a thing as a wave function, and they'll think, oh, how silly, that they believed in electrons and wave functions and things. We have this new framework which mathematically preserves the structure of the old framework. That's crucial, right? So when we make general relativity, for example, contained within general relativity as a limiting case is Newton's theory of gravity. But general relativity puts forward a geometrical picture of gravity. It's totally different from a sort of ontological point of view, from the perspective of what's actually happening. Relativity is making claims that are just totally different from the ontological picture of Newtonian mechanics. And so I think that the sort of pessimistic meta-induction says that this process will keep happening to us.
Yeah,
now that might be a bit previous to assume, but I think that's a sort of interesting take, at least.
I guess that is really fair to sort of bring it up in terms of like what we want as humans in our solutions. But I do think that like I think it's also important to note that there is a reason why analytical solutions tend to be favored, and that's because I guess sometimes the numerics will reveal new physics or have more explanatory power than they were expected to, but oftentimes very powerful analytical results tell us things about the universe or our reality, or at least the current portion that we understand of it. It tells us more about it than we were expecting. Sort of at the beginning of the beginning of the journey to arrive at that result.
Yeah, there's a sort of strong semantic component to this, which is that it's this question of okay, so what I want to sort of say is that computational physics sort of straddles experiment and theory in the following sense. I can do an experiment. For example, I can examine the resistance in a Hall material. So I've got a conductor, I've got a magnetic field going along, say, the x-axis. I apply a magnetic field, and I examine resistance in the y-axis, and I notice that resistance is quantized, the Hall effect. This is a so-called Hall effect. Okay, so I can do an experiment and see that that's happening. And then what a physicist wants to ask is something like, why is that happening?
Yeah.
And what a physicist really means when they say, why is that happening, is they want a model where each component in the model in the mind of the physicist sort of represents something in the material, so they want a model that represents the electrons, or represents the charge carriers, whatever they might be, and sort of offers predictive power. And that's what it means to answer a why question. Well, in like fashion, I was actually just reading some work today, some studies that were being done on this model, the TJ model on a honeycomb lattice. And so there were numerical results that suggested that this model exhibited this superconductor insulator phase transition.
Yeah.
And then a few years later, a subsequent paper was published purporting to offer a theoretical explanation, an analytical explanation for how this is happening. And so that would be an example of where the numerics are sort of not giving you the why, they're sort of giving you the phenomenon itself. They're saying, in this theoretical context, this behavior shows up. Now let's set about getting the why answer, which is always a sort of analytical answer, almost by definition. When we say why, we really want this kind of analytical explanation. And I think, as Oyle's actually pointing out, a lot of that has to do with the desire to connect physics in different areas. When we have a coherent analytical framework, we can draw interesting analogies. We can say, oh, an electron in a material behaves like as if it's an electron with a different mass and a different charge, and that's how we can explain things like the optical response of the material, or the electric response of the material to an applied field.
Yeah.
Yeah.
It's all very fair. The connection. Yeah, the connections between different areas of physics are. I guess they're most obvious in the analytics. So that's definitely fair.
But I think it is fair to say that one kind of hierarchy that we can comment on, and maybe it's worth mentioning this for the undergrads. You will encounter people sometimes, and I know a few of them, who don't just feel that an analytical solution is offering a why. They sort of feel that because of this fact, the analytical work is somehow a higher calling. Yeah. There's a kind of real ego that goes into certain branches of physics, maybe every branch of physics is susceptible to this kind of ego, but a certain kind of ego that wants to say, my part of physics is more physics than your part of physics. You know, the part of physics you're doing just isn't as important. And I think that that really is nonsense. That's just utter nonsense. You
Absolutely.
know, we need people doing everything. We need people doing experiments. We need people doing numerics. We need people doing analytics. These are all pieces of the puzzle that get us to better explanations. And so for those people watching who want to go into numerics, if it ever happens that you encounter someone who works on the analytic side of things and they just don't have respect for numerical physics, they're wrong. They're just plain wrong. The work you're doing is very important. It's crucial. Sometimes it's the only way for us to learn that a new phenomenon is even happening in a model. It's the only way for the analytical folks to understand what they should be focusing on.
Yeah.
Sometimes it's the only way to corroborate what the analytical folks are predicting. So
yeah, Gabrielle. Every career has an ego thing. That's definitely true. But some of these folks, it seems to be very particular with them, right? Like you hear the popular phrase, like you're looking into the eyes of God or something like that.
I think that there's a real, I'm going to use the word propaganda. There's a real sort of propaganda in science about what kind of science is interesting, what kind of science is useful. And there are many things that drive and shape how this discussion goes down. But I think that hierarchies within science are just aside from any sort of moral opposition I might have to them, I think that one of the strongest things I can say is that they're just counterproductive. It is
Absolutely.
not to be condescending to the people who are helping you. You know, science is a collaborative effort. You need people working together, and that involves respecting the ability of other people to contribute to the conversation. And so I think that the more that we can sort of bust down this narrative of hierarchies within science, hierarchies within fields of science, the better off we're all going to be. We're all going to learn more if we can value the contributions that everyone is making.
It perhaps a close the door on this discussion. It often comes from people who are sort of ignorant to how difficult it is to simulate and run some of these computational programs. To sort of put together an algorithm that takes maybe a year to get off the ground, and how difficult that actually is. It certainly comes from a place of ignorance sometimes.
Yeah, I definitely agree with Gabriella. You know, it's just sort of ego boost nonsense, and we should all try to overcome it, and we will all live richer lives for it, I think.
Every person out there who is really good at the mathematical physics side or the analytical side needs a friend or many friends. Collaborators that are also very good computational physicists. That type of collaboration is incredibly important for the development of theoretical physics.
I think also I want to maybe Gabrielle's comment is sort of inspiring me here to go a step further and to say that I think that within science as a whole, we need to maybe take a bit of a step back and appreciate that other subjects, so-called soft sciences, arts subjects, have a great deal of merit and value. And there is a prevalent feeling, I think, amongst people who do science. I certainly was inculcated with this when I
started
my undergraduate experience, a sort of superiority complex that you're doing the quote unquote the hard science, and other intellectual endeavors just aren't as worthy. That is also nonsense, and I think that we are worse off for believing that. And it also, sorry.
Oh, sorry. I was just agreeing with you. You often hear, there's like a hierarchy. Like, physicists think they're better than engineers and biologists, which I definitely don't. Like those are very difficult fields that I probably wouldn't be successful in.
Yeah.
And then mathematicians, perhaps rightfully come in and remind the physicists that all their tricks are actually not theirs.
Not helpful. We as a sort of society, we need everyone to offer their best.
I think what you all just said is a pretty common. I think that would be competing for the sentiment of a lot of physicists, unfortunately.
Right. Yeah, I think definitely a lot of folks adopt that perspective. So we can all be a bit more magnanimous in our attribution of praise and value for other endeavors outside of physics, outside of science, even I think.
Yeah, absolutely. I definitely agree with that. Everyone, you know, it's really tough to know how difficult something is unless you are actively doing it. So making a judgment call on basically anything is perhaps not coming from a place of a negative judgment call, anyways.
I love this comment by Marson. I hope I'm pronouncing that correctly. Especially this part, the most difficult part is to understand if your physics and algorithm combination is correct. I think that that's such a relatable struggle for any of us who have worked in some numerical field. You get your model out, you get your results out, and then you're looking at them and you're asking, is this a numerical artifact? Is this
Yeah.
real science? I think absolutely that's what are some of the cases, John, where you've have you ever gotten to the end of an algorithm and you've had a result come out and you've wondered to yourself, did I just discover something very interesting or did I just make a terrible, terrible mistake?
So before I answer that, I just want to add one thing to the conversation for Marston's thing is that one of the most tedious things about numerics, but it's absolutely necessary, and you have to do this to be academically honest, is that at every single step, you need to try to have some form of sanity check, right? Because you
Right.
complete the algorithm, right? And then you're like, wow, that was so hard, and I'm so happy my code compiles now and it's giving me results. But then you realize that you actually need to go back and perhaps perhaps there's some test case that you know the exact solution to, etc. You need to go face reality and test to see whether or not it's right, if such a thing exists. Um, for results where I wasn't sure if I found new physics or not, unless I'm forgetting something that you have off the top of your head. I'm usually here's a story where I wasn't aware of physics, and it inspired my first sort of popular video on this channel, the negative temperature thing. So I was collaborating with someone from Western University in London, Ontario, and we were convinced. So he was calculating temperatures. It was to do with eigenstate thermalization. So at particular energies, he was calculating the corresponding temperature numerically, and he kept getting negative temperatures. And I was like, that doesn't make any sense. Like temperature's not negative. So we went through and we tore his code apart. We tested everything. We ran all of these tests. And then one day I was like, wait, what if temperature could, like, what if it's just my understanding of temperature that's wrong? And that turned out to be the thing, and I got sort of interested in the topic, and then that's how that first video sort of popped into my head. So I didn't really think I discovered new physics. I was just unaware of physics, and it caused about a month's waste of time.
Right. That's very good. That's very good. I think Oil's asking a great question, which is what happens if you don't have a known test case available in your model? I have to say, I don't know if that really ever happens in the models that John and I studied, from the point of view that you always can do at least an exact diagonalization. So you can always, I'd be very interested to hear what the problem that you're looking at is, or what the model you're looking at is. But usually a couple of ways of doing these checks exist. So in the numerics world, in the condensed matter numerics world, an ED is always going to be sitting there. You can always do an ED to corroborate a Monte Carlo or a DMRG that you've written. Sometimes you have an old ED and you use it to corroborate part of a new ED that uses some new method or some new set of symmetries, and then that's how you do the corroboration. If you're doing an analytical calculation, maybe one where an ED just isn't tractable for the sort of system that you're looking at, maybe you're not looking at a system where ED is applicable, then taking the limiting cases, take cases where, the infinite temperature limit, the zero temperature limit, the zero interaction limit, take limiting cases and really try to interrogate whether or not you're getting things that sort of make sense and are sensible. And these are sort of ways that you you can fix things. I did one paper once with a colleague of mine. It was a rather complicated calculation. We were looking at we were making an analytical ansatz for the wave function in this model called the Hamiltonian mean field model. And the ansatz that we were making was a so-called large N expansion. So there are many ways of doing these expansions. What basically happens is that you have a model, you have a system, and the model that you're using to describe the system doesn't have a natural parameter that you can expand in. So maybe you're familiar from your quantum mechanics course with a situation where I have a solvable Hamiltonian and I add a perturbation to it and I make my approximation in powers of the perturbing component of the Hamiltonian. Sometimes you can't do that. Sometimes you have to sort of engineer a small component. And you can do this using these so-called large N expansions. N might be the number of particles in your system, but it might also be the size of the symmetry group that describes the system. So in a spin case, spin 1/2 particles are described by an SU2 symmetry. But maybe you imagine instead a model that's described by an SUN symmetry, and you take N to be enormous. And at the end of the calculation, you set N to be 2 or whatever it is that you're actually interested in. These techniques sometimes really work, amazingly enough. And so we did this calculation, and the only ways that we could check it were by doing things like taking limiting cases, trying to see that if we recovered the case that was exactly solvable when we sort of took N to be infinitely big, or things of this nature, to sort of try to corroborate the result that we had. But it isn't always so easy, certainly.
Yeah, definitely. Just to add to that, like if you're, I guess I'd be really interested to hear, briefly, what you're working on, because if it's something like an ODE or, a partial differential equation, then there's oftentimes simplifications, and you're in, like, let's say you're doing numerics on it. There's usually a term in your equation that you can drop and have the expression be solvable, I guess that would be the biggest thing. Or as James was saying, taking limiting cases, you could even solve it, for small time steps by hand to sort of check to make sure that if you do this by hand, what are the numbers that my algorithm should be giving out. Like that's definitely a sanity check, doing a little bit of it by hand. And then of course taking limiting cases like James, you can say, if I start here, what's the end game behavior that I expect, like for, it's a very simple example, but for the heat equation, it's probably easy to convince yourself that, heat should eventually spread uniformly over the system. And perhaps there's similar intuition that you could derive from your expression, but I guess it would be difficult to go. Depending on the model, we could probably talk about this for forever, or perhaps it's very difficult to find a sanity check for your model. I guess that's also possible.
It's something you always want to do, right? Because the last thing you want is to publish something, especially when you're in one of my profs. Eduardo Martinez once said, the problem with publications is that if you make a mistake, it's there forever. As a student, you make a mistake and it's gone. It disappears. But when you're a professor or a grad student or a postdoc and you publish a mistake, it's forever. It's always going to be up there unless you publish an errata, and everyone will know that you made an errata. And so you really do want to sort of make sure you're corroborating your result, especially if it's a controversial result, with something that you're certain of.
So you'll says we did some cellular. So you did end up getting a limit to test. So that's always good. So sometimes it is difficult to sort of look for what that limit that limit should be. One of the interesting things about our supervisor is that he seems to almost be able to tell whether or not your code is doing the right thing by looking at plots you make. He sort of like immediately has this intuition and understanding of like, oh yeah, that's what that should look like, or no, something's wrong here. You need to.
With time and practice, you really can start to sort of pick out the numerical artifacts, the things that just aren't quite right. You get practiced enough that you're able to sort of tell when something is fishy. and there are sort of standard checks whenever you get deep into any field. There are sort of standard pieces of knowledge about the models you're studying that are always a cue, and I think that comes with a great deal of experience and implementing different algorithms and studying different related systems. You sort of build up this library of expected behaviors.
Yeah, I definitely agree, Gabrielle. So sometimes making sure that your maybe base results are even correct can take twice as long, and it's very, sometimes it can be extremely tedious. But you just have to hold yourself to a high standard and make sure that you're doing it right.
Definitely.
So it's an important part of being a scientist, I guess. Even though it's not a fun part, it's definitely not. It's not a part of science that I like doing, but it's something that you always have to force yourself. James, I'm curious. So you led off this discussion asking if I ever thought I discovered new physics. Have you ever been in that situation where you thought you may have stumbled upon something that?
Yeah, there are things that sort of like haunt me to this day about. So there's it's not a numerical. It's sort of numerical, but I mean it's one of these situations where you can write down an exact expression and then you just numerically integrate it. So it's not really a numerical problem in the spirit that we're discussing. But there's a particular model, the Kitaev honeycomb model, which when you examine certain information theoretic quantities in this model as a function of its parameter space. Across a sort of broad range of the literature, you get these interesting artifacts. In the gapless phase, you see these divergences, they look like divergences, these peaks that happen quite densely in this phase before you get to the phase transition proper. And no one has an explanation for this. No one really offers any clear explanation for the relevance of this, what this means, why this is sitting there. And I just think that that's fascinating. Like one wonders, where these kinds of things come from, and so that would be an example of some physics that I'd be very interested to hear a sort of complete explanation of. And as far as I'm aware, no one has offered one in the literature yet. So there are things like that where when you encounter them at first, you wonder, am I doing something wrong? Is the first thing you always think, and then you see that basically everyone is finding the same effect, and then you begin to wonder if maybe there isn't something a bit more interesting to it.
Yeah.
And so, yeah, I think this can happen quite often.
Yeah, that's definitely fair. I remember while you were going through this, those I feel like you paid extra attention to those numerical integrals. It seemed like we were talking about it every week.
Yeah, that was a big, rather involved moment of my life.
That's definitely fair. So I have an interesting question for you, and then perhaps I can expand on my experience as well. So what was your sort of first exposure to programming, and sort of at what point did you realize that that you think doing computational research would be a good fit for you?
I interviewed with two professors, basically.
So this is fourth year. Just to make this clear. Okay.
Yeah. So after undergrad, I had done both of the computational physics courses at Waterloo, which ostensibly teach you Python and C. And I learned almost nothing from the C++ course, I have to confess to you, but I had it on my CV nonetheless. And so I applied to McMaster, and I interviewed with two professors. One of them worked in the analytic side of things, and the other the computational side of things, and the person who did the computational side of things had funding. I ended up working with them, and we so then that first summer I was here, I basically from the ground up sort of taught myself the ins and outs of C and C++, which
just a shout out. I would say that I'm competent at C++, but I certainly do not compare to James's sort of skill and knowledge of the language. He's an excellent programmer.
That's a very generous thing to say. I really love programming. It's a great joy, I think, of grad school for me that I've had an opportunity to hone that skill. But I also fell into the trap early on of being really disparaged from embracing my numerical side by these sort of arrogant analytical physicists. And so I now have a sort of smattering of papers. I've got some papers where I do numerical techniques and other papers where I've done analytical techniques, and sort of play with both of these things. And I think for me at core level, what I'm really excited about is the answer to the question I'm curious about at the moment. So whether I have to do a numerical method or work on some analytical technique to get that answer, although I'd be kidding myself if I tried to pretend that I was anything like as competent as the analytical folks are at their techniques. I'm definitely much more competent and experienced working with numerical methods than with analytical methods. Yeah. But I think it was really sort of something where you just kind of, you know so little as an undergrad. I knew so little as an undergrad, and I think this speaks for a lot of people's experience. You know so little about what the field looks like, what it looks like to really work on these problems all day long, what techniques you're going to use. And so whatever prejudices you might have about what you're going to like and what you're not going to like, I think very often are going to be upended by the real experience when you're actually, for example, I have a friend of ours who started off as a colleague of mine directly working in the same research group, sort of on the numerical side of things, really desperately wanted to work with this professor who does analytical techniques, and actually sort of camped outside of his office and just with great determination and zeal was able to get a position with this research group doing analytical work, and has been doing that now for several years. And I think now is contemplating going back into the numerical side of things, maybe doing artificial intelligence work, because I think that they found that particular flavor of analytical work just really didn't click for them. And so I think that's something that, I don't think that it was a mistake for that person to do that. I think that you should dive into the thing you're interested in, try it out, and it's okay not to stick with it forever. Life is about learning and trying new things, and I think that's perfectly reasonable. But I think we shouldn't be so hard on ourselves. If we go in for one set of techniques and we find that the thing we thought we really wanted to do just wasn't for us, there's no shame in that. There's nothing wrong with trying some new technique, trying some new set of methods. I think, in fact, that actually makes you a much more well-rounded researcher, because you can just talk to more people. You can understand more results. You can see where your work fits in with the bigger ecosystem, all the better for trying out a few different techniques. And your PhD really is the time to do that.
That's really interesting. For me, it was in second year. I had a professor of so where I went to school, the applied math department had all of the theoretical physicists. So they often taught math courses and not physics courses. And in my second year, maybe it was like the third calculus I took, maybe the fourth one. I had a theoretical physicist for my professor, and one of his office hours I went in and I was like, and like this is not the same person from the story. Like this is basically a common theme from me is that I will go in and pick people's brains all the time about what they think is the best path forward, because I know that they know more than me, and I just want to sample opinions until I can come to some type of consensus. Sometimes, and in particular, I was really interested throughout my entire undergrad about how to plan and structure my undergrad so that I'd come into grad school with the best tools to solve physics problems. And so I went in and I asked him the same question that I asked the professor from the story at the beginning of the video, and he said he doesn't take grad students that don't have extensive numerical background, because he doesn't have numerical background, and then there are just a lot of questions that he can't do without people with numerical backgrounds. So like as of right now, he wouldn't consider someone who didn't have extensive experience in computational in computational physics. So at that point I was like, okay, I need to basically be taking some type of computational course every semester. And luckily that's the applied math department there was like, there was theoretical physicists, mathematical biologists, and then people who worked on numerical analysis type problems. And of course I'm probably forgetting some subjects there, but so I was definitely in the right place to take that advice seriously, and I definitely appreciate the sentiment that you want to be able to just answer the problems you're interested in, right? Like when you're doing analytical work, oftentimes you have to say, can I answer this problem? No. Okay. Next problem. Can I answer this problem? No. Okay. Or at least like for mathematical physics, when you're talking about, writing theorems and things like that, sometimes you just don't have the tools, right? But like I don't want to have to do that. I want to say I want to learn more about this, and I want, like, so I'll come at it with whatever. Like I want to. I don't have the skills to do this as of right now. There's many things I want to learn: new numerical techniques, new analytical techniques. And that feeling will probably never end. I'll probably die being like, oh, I should read this textbook for for these techniques, right? But yeah,
there's always more to learn. I think one piece of advice maybe to undergrads is follow your passion, right? This is one of these pieces of advice that people never tire of saying to people who are sort of at a younger stage than they are. But I really think, if you want to love what you're doing and you want to sort of have the most unique and impactful experience, I think you've got to just pursue the things you're passionate about with abandon, and it's good to be pragmatic. Obviously, some people that really works for them, thinking about trying to study a certain area because it's going to be useful later on. I know that when I was getting into numerics, a lot of folks would say things like, well, that'll be great for a job in industry after, or something along these kinds of lines.
Well, that's what our supervisor said to me.
Yeah, our supervisor shared that, and I think our supervisor is quite correct in that. But I think also, if you do analytical field theory, you're going to be able to get a job in industry after. It's going to be fine.
Yeah.
Choose to do the things that you want to do because you see them as valuable for you. Maybe that's because of their professional gain, and that's fine. But really, I think prioritize that. Don't be don't feel like you have to sort of cleave to you have to study X and you have to study Y, and these are the ways to do good work. It's important you feel passionate about the work you're doing, that you feel curious about it, or else you're going to have a hard time maintaining the motivation, especially in graduate school, I think.
Yeah, that's some good advice. So Yule said it's actually insanely hard to get into a field. Known papers, jargon, analytical / computational techniques, important results. Nobody can tell you all of that. That is honestly so true. There is such a barrier to getting involved into questions that you want to potentially contribute to. That's why choice of supervisor is obviously extremely important. One for getting into the field you want to do research in, but also someone who's willing to sit down with you and make sure that you get exposed to the information that you should be exposed to, so that instead of being someone that you do work for them and you solve problems for them, actually building you up into someone who is aware of all the jargon and who is aware of all the important results that are going on.
Yeah, absolutely. You need a supervisor who makes you feel comfortable to ask questions.
Yeah, and see, that seems sort of straightforward, but that's not always the case, which is unfortunate about academia. Gabriel says the key to success is failure, they say. Yeah, I definitely agree with that. You learn more when you're willing to just set yourself up for failure. I never make results. I never make progress on physics problems when I just sit there thinking about how I should start. Sort of. It's once I actually sit down and I'm like, you know what, I'm just gonna code, and I'm going to put my idea down there. We're gonna see if it works or not, or I'm gonna start playing around with symbols on a page to sort of think about this analytical problem.
Absolutely. You need to just start sometimes.
So Yule says the only serious question I've ever been asked for a thesis is, can you program? Yeah, I honestly, that is basically when I guess for the only two supervisors I've ever worked for, I think that was the big question for both of them as well. It's also that programming solutions to problems is also probably the easier way to get first exposure to problems, I would say.
Depends. I think that can depend on the problem you're working
Yeah,
on.
at least all the ones that I've been exposed to, I initially, at least maybe this is just my intuition at play here, but I really appreciate learning the subject numerically first, because it sort of gives you a lot of intuition about how things sort of work out. So Pontus says, do you read any mathematics aside from the stuff you learn in the standard curriculum, uh, for reasons other than learning some specific method? So I do. So okay. So when you say the standard curriculum, that might not apply directly to me because I did my undergraduate degree in the applied math department. So I did a lot more math than your typical physics student. Um, but for my current maybe it's around here somewhere. Oh, it's not. But yeah, so I definitely do. Perhaps this sort of falls into your category of specific method, but there's areas of mathematical physics that I definitely want to understand the results just to understand them, but also because I feel like I can't properly insert myself into certain conversations, and potentially do research in certain areas without specific background. So I guess that's outside of the standard curriculum. But I guess it is sort of trying to understand a specific method because like the which math I'm learning is being guided by my research interests. So perhaps the answer is I don't know. Maybe. Probably. Yeah, I guess 50-50. Yeah, I don't know.
I I love math. I read I try to learn about math all the time. Math that isn't directly related to the problems I'm working on. As in grad school took a bunch of grad courses in areas of math that I don't use most of the time in my daily research. But yeah, I definitely think learning more about the language. Because the thing is, right, like as a physicist, what you're kind of trying to do. This is my romantic idea of what you're doing as a physicist, right? You're sort of trying to find new mathematical structure in the universe, right? Yeah, I mean, well, 100%.
You'll need group theory. Absolutely, that comes up everywhere.
That's ubiquitous. You need group theory. I took a group theory course in my undergrad. I took a group theory course in grad school. 100% group theory is wonderful.
And, and,
Learning.
and I guess in undergrad you do get an exposure in the standard curriculum, at least here, to computational physics, but certainly not enough in my opinion. I think you should get more exposure to it, at least at the undergrad degree I went to, my friends in the physics department. But then for group theory, if you go through a physics undergrad, I don't know about you, James, but that was not even on the radar of basically anyone taking physics courses.
I think, yeah. So where I went to where I did my undergrad, everyone who was serious about theoretical physics in the physics program knew about group theory and took at least one group theory course, or was at least exposed to group theory through. We had a required course called quantum theory, so we had 3 quantum mechanics courses, and then we also had a quantum theory course. And the quantum theory course introduced you to Lie algebras, Lie groups, how they relate to the structure of quantum mechanics, and so on. And so that was
I
very
I took abstract algebra, and I guess to my physics friends who I like, I don't know, I don't think they were very serious about theory. The department was very small, so I don't have a very large sample, but it was certainly treated as like sort of an abnormal course for someone interested in physics to take.
if you do particle theory or GR, you basically have to learn. I mean, it becomes when you do. That was actually the other place that you do group theory. If you take the 4th-year particle course at Waterloo, the introductory chapter to the course is group theory.
Oh, that's interesting.
Yeah, because particle physics, that's just how particle physics is built, right? Like particle physics, in group theory, particles live in the representation space of the group that the action respects. And so understanding the group theoretic structure of these things is crucial. Otherwise, you can't do particle physics at all.
Yeah, so just to elaborate perhaps on how things work here in Canada. I don't know if it works like this in other places, but the Ontario government, I believe it is, they mandate that your classes need to have a specific student number, like a specific number of students in the classes for the classes to really be offered and funded. properly, or maybe it just comes from the universities, but the universities seem to have the same numbers, so I imagine it's something more centralized in them. So when you go to, often people ask the question, is it better to go to a school that has a big physics department or a small physics department? And usually, when you go to a big physics department, there's more areas of research that you'll probably get exposed to, more opportunities to do those resources, or perhaps not more opportunities because it's more competitive. But an added bonus in Canada, at least, is that when you get into fourth year, you do have courses like general relativity, like particle physics, and things like this. At my school, by the time you get to fourth year, the class sizes have gotten so small that they can basically only offer just enough courses for everyone to graduate. So none of these courses, these so-called specialty courses of general relativity and particle physics that I think should be relatively standard in someone's education, like these things don't get offered. So it's a huge downside. The upside is that basically research opportunities and internship opportunities are very abundant, so everyone gets opportunities to do lots of research. When I sat down in my QFT course, I never had any serious lectures about group theory. QFT was not a lot of fun. Let's put it like that.
Okay. Yeah, that's doing those courses, if you're an undergrad and you haven't gotten up to the upper year yet where you're going to do QFT and stuff like that, if you put the time in to do some math courses earlier on that are outside of the required math courses, you're doing yourself a big favor if you want to do theory, for sure.
Yeah, that's definitely true, and it seems like, oddly enough, I can't remember. I found that a lot of my physics friends didn't take partial differential equations for whatever reason, but that you solve so many, like in electromagnetism, like at some point it just becomes PDEs. So for them it was very difficult because you had to learn all these concepts sort of on the fly as you were learning physical concepts as well. But taking as many, I don't know, I'm biased, but I think you should take as many, if you're interested in theory, you should take as many math courses as you can get your hands on. Of course, pointed towards topics that you think will be interesting and useful for physics, I guess.
Yeah, definitely.
So I guess it's 8:07. We had this basically scheduled for an hour. Great chat, guys. Thank you for everyone who came out. Thanks to James for coming in and chatting with us again. It's definitely been a good time. There won't be a stream next week, but we'll resume them the following week for the foreseeable future. Pontus says, I'm still in undergrad Europe, but it seems like most math after first year is picked up on the fly, but the line between mathematician and physicist can be blurry sometimes. And Marson says, it's interesting that you have a choice in USA to take or to not take some fundamental.
I think I might have to sign off here, my friends, but I haven't had dinner yet. Mega chili sauce coming in with a cool question at the end here.
Yeah, I feel bad because I sort of have to sign off here too.
Well, perhaps Mega chili sauce can come for our stream in 2 weeks and we can address this question.
Yeah. My apologies, guys. I sort of have to hop off here as well. It was great talking to everyone. Thanks again. To everyone, I think, yeah. So have a good night, everyone. See you later. I don't know how to sign off properly, but have a good night.
Bye all.